Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 12, VHDL Design II, for the course Digital Logic Design, Digital Systems, or Digital Electronics, for Chapter 3, Combinational Networks. And this is the last lecture for Chapter 3. The next slide is a disclaimer for you to read. There are many references in digital logic design. I list 3 of them here. The contents for Chapter 3 are combinational networks. We talked about Karnaugh maps, 2 variable K maps, 3 variable K maps, 4 variable K maps, 5 variable K maps, and 6 variable K maps. We talked about incompletely specified functions and complement of a function. We talked about standard forms and canonical forms, sum of products and product of sums, and max terms and min terms. We talked about 2-level implementations, and we found out that the NAND gates are universal gates as well as the NOR gates. Plotting functions on the map is a process which is extremely useful to cover all the techniques and methodologies that we used in Boolean algebra, like the conversion function from one form to another, and so on and so forth. We talked about design of multiple output combinational networks, and we took some examples of this topic. We talked about variable dependent functions and map intervariables. Today we'll talk about VHDL Design II. Design of combinational network using VHDL. VHDL design allows the designer to implement, simulate, and synthesize switching Boolean functions in any and all forms of representations, including as a truth table. Without any simplification or minimization, we can implement function as a truth table in VHDL, and we can build the hardware to implement this function or to synthesize this function or any Boolean function. The function could be a minimal sum of products, or minimal product of sum, or canonical sum of midterms, or canonical product of max terms, and other non-canonical, non-standard forms. So in any form, we can use VHDL to implement the function, to simulate it, to synthesize it, and to dump it complex logic device, PGA, and so on and so forth. In addition, functions, Boolean functions or the switching functions can be implemented at different levels of abstractions like gate level, RTL, behavioral architecture, which is the least level of abstraction. As an example, we'll look at the design of BCD to 7-segment decoder using VHDL. So this is VHDL using design using the truth table of the converter. In the truth table, we have the inputs W, X, Y, Z, and the inputs to the 7 segments, assuming the 7-segment display, as we have seen it in a previous lecture. The 7 segments is A, B, C, D, E, F, and G. Now, if we would like to display 0, and if the 7-segment display is common anode, we need all zeros for all the segments except the segment G, which is the one in the center. We needed 1 to not get light out of the segment. So by this, we will get a 0. And so on and so forth. Actually, for number 1, 2, and so on, if you check this. So this is a representation of 7-segment display common anode. It means the anode is taken to plus 5 volt positive voltage source. Now, how we represent this truth table in a VHDL code, and this is very, very simple. We go actually define the library IEEE that standard that underscore logic and underscore 64.0 entity. We called it SEG7, 7-segment display, and is the port, the input port will define it BCD. It is WXYZ. If you remember, if you define it BCD, binary coded decimal, you can define it as a 4-bit vector. So this is an input port in standard logic vector 3 down to 0. It means we have BCD3, BCD2, BCD between parentheses 1 and BCD between parentheses 0. And the output LEDs, the LEDs will be out, and also the standard logic vector 1 to 7, because we have 7 outputs. The segment A, B, C, D, E, F, G, what we called it here LEDs for simplicity, and it is standard logic vector 1 to 7. Then I will end my entity name SEG7. Architecture behavioral of SEG7 as we begin. The process between parentheses BCD. Now, why BCD? Because BCD changes values. The input changes values. So begin, we will use a case in this process. See, the process will start with begin and will end with end the process. If we use case, the case will start by the word case and end case. The case here, BCD, within the process, when we have 0, 0, 0, it means when the inputs are 0, 0, 0, this will imply LEDs will be assigned to 0, 0, 0, 0, 0, 1. So as you see, this is only G, A, B, C, D, E, F, G. Only G will be 1. And this is really the direct implementation of the truth table. So we assign those values. If I have 0, 0, 0, 1, I will assign 1, 0, 0, 1, 1, 1. And this came from the truth table, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1. And so on and so forth. If 1, 0, 0, if the input 1, 0, 0, 1, the output will be 0, 0, 0, 1, 0, 0. And this is, you see it at the last line. When 1, 0, 0, 1 at number 9, the ABCD will be 0, 0, 0, 0, 1, 0, 0. So only E will be 1. Now, all the others they don't care, so the LEDs we will assign them dash 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 7 dashes, which is indication for do not care. I don't care any value to be assigned if other input occurred outside the zone between 0 to 9, and this non-BCD incoming, which will not take place usually. So we will have the LEDs will be assigned to don't care. So again, we started with case BCD. I will say end case. We started with process. I have to end the process. We started with architecture behavioral. I will end. I say end behavioral. I don't say end architecture. End the architecture name, which is behavioral. And we have ended really the program. And once we have a pure entity, we can assemble this and generate the netlist file, and you can dump it on chip if you want to, on a device, and you can test it. You can simulate it, you can test it, and you have a complete design for the VHDL code for BCD to 7-segment code. As you see, it's extremely easy. Now, we can take the truth table to K-maps and we minimize those outputs A, B, C, D, E, F, and G. So when we minimize them, we have A, W prime or bar, X prime, Y prime, and Z, or X, Y prime, Z prime. The same thing with B. So when we minimize them, we get A, B, C, D, E, F, G. We have to generate variable came out for every output, and we do the minimization as we learned, and we have the function as a minimized sum of products. So once I have those functions, I can generate the VHDL code by implementing those functions as logic equation using a sum of products representation, and this is coming next slide. So this is a higher level of abstraction than truth table, but it is less than the gate level abstraction. It's called LTL level of abstraction. So again, we'll define the library IEEE, use IEEE.std underscore logic underscore 64.0. Entity reg7 version 2 v2 is the inputs here. We define the W, X, Y, Z in standard logic. So those will be defined as bits, not as a vector as we did it previously. And the output is A, B, C, D, E, F, G out. And in the entity names, which is reg7 v2. Architecture RTL of reg7 v2 is we begin. Then we end RTL the architecture. And those will be the logic equation for A, B, C, D, E, F, and G. Let's check A. What's A? A, we said not W, not X. This is how we write it in VHDL. W prime, W bar, is not W, not X, not Y, and Z. Or X, not Y, not Z. So how we write it? We write it not W and not X and not Y and Z between parentheses, or the second product term, which is X and not Y and not Z. It's beautiful. We've done. Semicolon. Done with this equation. The same thing with B. B is X and not Y and Z. X and Y and not Z. And this is B. So B, X and not Y and Z, or X and Y and not Z. And so on and so forth. So we implement all these equations, A, B, C, D, E, F, G, and RTL, and let the VHDL take care of that process. And we can simulate the program, we can dump it on a chip, generate the netlist file, dump it on a chip. And here we go, we have the converter, which we can test practically in the lab if we want to. Now, also, we can generate a gate level. This is slightly more complicated and very useful. Very useful because if we do counter with delays, we can add delay elements, we can compensate for the delay. And when you design on the gate level, the design to be in all NAND gates or gates, as you can see here. So this is the implementation of A, the hardware implementation for A, using all NAND gates. We needed inverters for W, X, Y, and Z, and we have a 2-input NAND gate used as inverters. And we have product terms that we can generate here by using a 4-input. We need a 4-input NAND gate, we need 3-input NAND gate, and we need a 2-input NAND gate. G1, G2, G3, G4, and G7 are 2-input NAND gates, while G5 is a 4-input NAND gate, and G6 is a 3-input NAND gate. And we see actually a vector called S. S from 1 to 6. Those are neither inputs nor outputs, so we call them intermediary signals. Signals within the hardware. So I have S1 coming out of gate 1, S2 coming out of gate 2, S3 coming out of gate 3, S4 coming out of gate 4, and S5 is the output of gate 5, and S6 is the output of gate 6. And those will go to the gate 7 to generate A. So how we design this? We will design this in a design called hierarchy. What we mean by this? We need to design a 2-input NAND gate we need a 3-input NAND gate, and we need a 4-input NAND gate. Then these, we call them components. These components, we can have them in a package, or we don't have to have them in a package. We can write the code without a package. We can put them in a package. We can package them, which is much better because we can use the package anytime that we need by linking the work library. I will show you in a second. Or we can not have a package. We don't have to define a package. We define a component within the program, and we have to do this process every time we need those components, namely G1, G2, G3, G5, G6, 3-input, 4-input NAND gate, 3-input NAND gate, and 2-input NAND gate. So we can do it either with package or without package. But the main important thing, we have to define those components. So we have a 2-input NAND gate, we have to define a 3-input NAND gate and a 4-input NAND gate, and we have to compile the VHDL code for each component. So we'll have the compilation result on your machine, on your computer, before you go to implement A, okay? Or we can have them in the same program, also will work. So at the end of the program, we'll have these components. Component number 1 is a 2-input NAND gate. We use the name before NAND 2 too. It's a behavioral approach. I have 2 inputs A and B in standard logic, and have F is out in standard logic. I will end the entity. The architectural behavioral of NAND 2 underscore 2 is begin, process AB, begin. Compared with a truth table if A and B, then if both inputs are 1s, F will be 0, otherwise F will be 1, else F will be 1 all the time. I will end the process, because we have process A and B, end the process, and end architecture behavioral. We say end behavioral. So this is the program at 1. I have to compile it, or I have to put it at the end a program. Either it is better to compile it, then we can link it. I will show you how to do linking to use this component. So we did component number 1, which is a 2-input NAND gate, which we have it in G1, G2, G3, G4, and G7, all of them 2-input NAND gate. We need a 3-input NAND gate, which is G6, and we need a NAND gate, which is G5. So those are coming 2. Component number 2 is the 3-input NAND gate, where we have the inputs A, B, C in the standard logic. F is the output in NAND 3. Architecture behavior of NAND 3 is we begin process the inputs A, B, and A, B, C. We begin if A and B, if A is 1 and B is 1, we have to use quotations here, and C is 1, then I will assign F to 0. The assignment sign is small than and equal to 0 between code. This is binary data. Yes, else F will be 1. Any other values of ABC will generate at the output. And F and the process and behavioral, which is the architecture name. So once I have, again, this is component 2, which is a 3-input NAND gate. Component number 2, a 3-input NAND gate. Component number 3, which is a 4-input NAND gate. I have the inputs A, B, C, and D, NDD, NAND 4. F is the output in standard logic. I will end NAND 4. Architecture behavioral of NAND 4 is begin, process A, B, C, D. Begin. If A1, B is 1, C is 1, and D is 1, then F will be assigned to 0, else 1 will be assigned to F. I will end if, started, I have to end the process that I started, and end behavioral, which is the architecture. And by doing this, I implemented the 4-input NAND gate. Once I have all these, I will define those in a package. We said the package, it's a very premium and a very good approach to generate a package, because package will allow you to use these components as many as you want. because they will be in your library under library work. So package at library IEEE use IEEE standard logic 64 that all package components is. I will define each component at 2 version 2. There's code 2. I have the inputs A, B in standard logic. This is like the entity definition precisely, and F is the output standard logic in component 93. The inputs A, B, C in standard logic and F out in standard logic in component 94. A, B, C, D they will input and F is the output in component. Now I will say in the package which named components in, and I have a complete package program. Then I compile it, and once you compile it, the result of these components, you can instantiate them. It means you can pull them up and use them like subroutines saved in memory forever. And the library callback. So I would say library IEEE use IEEE standard logic 1164.0 library work use work.components.org use. This is very important. Library work use those two statements because the package is saved in the library work, and this work is on your compiler inside your processor on your computer only. Okay, so if you use a different computer, you have to repeat. You have to simulate package program and again. So I will use UAT component.l. Entity function A. Function A is for WXYZ and standard logic in function A. So I will end entity. So I have the WXYZ in, and I have A, small a is the output. Remember, we have not only A, we have A, B, C, D, E, F, G. If we wish, we can add this because what we are implementing only one of them now. Okay? Only A. So you can define the output as A, B, C, D, E, F, G, and we can define all the other functions. Okay? Now, remember we defined a signal, we called it S signal, S1, which is the output. The output, this is the signal here, S1, S2, S3, S4, S5, S6. All these signals, which is the output of the gates, those signals, they are not inputs, and they are not output signals. So, they are intermediary signals. So how we write them in the code? I will define it in the architecture. After the architecture declaration gate level, because we are implementing gate level. Function A is the entity name, remember, function A is signal S, standard logic vector 1 to 6, because we have S1 to S6. I will begin architecture, so we do, this is called instantiation statement with positional association. This is extremely important. So for instance, we go to gate 1. Gate 1, what we need? Gate 1, it is a 2-input. Gate 1 is an AND 2, 2. So it is a port map, and I have A, B, and the output F. A, B, in happen this is an inverter. The first gate, gate 1, is an inverter inverting W. So I have two inputs, W and W. W and W is not W, and the output is S1, and the output is S1. We look at the hardware. So when we instantiate it, I have W, and the output S1. I have X, G2, I have X, and the output S2. I have Y, and the output S3. I have Z, and the output S4 for G4. Okay. G5, the inputs are S1, S2, S3, and Z, and the output is S5. G6 is X, S3, S3, S4, and the output is S6. And G7, I have the inputs S5, S6, and A. And this is what we see it in the program. This is what we call it a positional association. Very important. One mistake will deem your design to be wrong. So I have the two inputs and output as 1, G2, XX, and the output as 2, YY, and the output as 3, G4, ZZ, and the output as 4. Those, all of them are 2-input NAND gate. In the 4-input NAND gate, I have S1, S2, S3, and Z, and the output is 5. In the 3-input AND gate, port map is X, S3 is 4, and the output is 6. In the last NAND gate, which is G7, it is a 2-input NAND gate. I have S5, S6, and the output is A. And this is what I'm looking for. And I will end the gate level, and by this we implemented A. We can add to this program the other outputs B, C, D, E, F, G, just we extended here with A, B, C, D, E, F, G, and we can generate all these gates with different outputs. Those in the, we add those statements in the architecture, okay, and we may need to assign different S's. Okay, we extend the vector as 1 because if we have different outputs, so we need to extend the S vector as well if we are using different S's with the other circuits. It depends on your design. Now, we said we can implement A without having a package. To do that, if I don't define this package program here, which is I highly recommend, because once you define it, all the components will be at library work. If you don't want to do that, you compile the program. So without package declaration, you in the program itself, you declare those components that you need to use. So component NAND 2, port A, B, and F, and component NAND 3, okay, port A, B, C, and F, and in component NAND 4, port A, B, C, D, and the output is F. This is came from like the entity definition. Under the architecture, you define component. After the signal declaration, you do this. Then you begin and you do the instantiation statement positional association as we did it. Okay, but here, the only thing here, we declared the component within the architectural statement and without the need to the package program. This program will not be needed if you do this. So I've shown you two approaches of hierarchy with package and without package. And again, I recommend the package very highly. And by this, we end lecture number 12. And this will be the end of chapter 3. I thank you so much. Please subscribe. Hopefully, I will see you very soon. Next lecture. Sincerely, Dr. Hassan. Bye.